Now we're not going to be sampling, we're going to be sampling quite the opposite. We'll be sampling a very small stream, a third order stream. Now we'll talk about large rivers first. So one way to call a river a large river is by how much water it puts out, how many meters per second. Okay. So number 6 on that list, I hope I can remember all these pictures. That's the Mississippi. I know I took that picture. Okay. That's the Yangtze. That's the yellow. It's not important that you know these. Okay, it's not. I'm just talking about there's something I'm going to be making from all this. That's the Parana, P-R-A-N-A, by discharge. Okay. That is the Orinoco, and that is the Amazon. Okay. Count down by length. Yellow. That's the Mississippi. The Yangtze. No, not that wasn't the Mississippi. Who is that? Okay, it's a long river, and that might be the Orinoco. It doesn't really matter. Okay. Number 2 by length is the Amazon, and the longest river in the world is the Nile. Okay, which is interesting because the Nile doesn't even play with discharge. It's right in the top of discharge. Why is the Nile, even though it's the longest river and drains out the Rift Valley, why is discharge so low? Yet the discharge on the Amazon is huge. It's kind of obvious in that picture.
So is it because of the difference in the plant life?
It's flowing through a desert.
Okay.
Evapotranspiration is big. And so you lose lots of water from the river to that way. Okay. Now, when it comes to discharge, by the way, let me go back to the discharge picture here. No, never mind. I can't get back. I want to go back to it. Okay. So, really, in the world, if you were to take the look at the top 10 rivers in terms of discharge, how many cubic meters per second they put out? You have the Amazon. If I take the next 2 through 10 and add up their discharge all as one number, it doesn't equal the Amazon. Okay. So Amazon is in a class by itself. There are small streams, mid-order rivers, large rivers, huge large rivers, and the Amazon is by itself. The Amazon puts out so much water that if you were at the mouth of the Amazon and were to go out to the ocean where you could no longer see the shore, 6 miles out, and you took a sample, it's fresh water. The river displaces the ocean out for a distance, 6 water. So it's basically stands by. There are places on the Amazon where you can't see the other side. It's huge. Okay. Another thing that large rivers have in common is they are the target of perturbation, meaning they have been managed heavily by humans. The primary reason for that is their role in navigation, the movement of supplies and all that. And these are some of the examples of perturbation on the Mississippi River. This is what is known as a wing dike or wing dam. Here, these are big rock walls that are put out into the river. And what they do is they force the flow of the river to stay in the main channel instead of going out to the sides. These areas sort of silt in behind it. And the purpose of that is to keep the water moving fast, so erosion, so it doesn't fill in. Because we want to support navigation, you have to keep it moving. This is a snag puller, so its job is to go up the river and pull out any large logs that are coming in. And this is riprap right through here. This is what they're doing here. This is a rock operation. They're putting riprap on the shores to keep the shores from sloughing in, which we put in sediment and affect navigation. Besides navigation, there are other ways the rivers are affected. Damming, turning a lendic system into a loadic system. This is a major perturbation. We'll talk about some of the problems that damming causes. This is a hydroelectric dam. So hydroelectric dams basically stop all flow, and this is Lake Mead, by the way. This is the Colorado River. They stop all flow, and then basically the flow comes out through a sluiceway, and what that does is turns turbines to make electricity. This is What you're seeing here is our river meanders, these little things you see here. This river used to meander, as we used to talk about, that rivers meander, but they've cut a channel so that the river goes straight through here. So that's channelization, big problem. Major problem in our stream is why our streams look like they look like. Okay. When we're gonna go into the Cane Creek today, it was never channelized. However, because the Obion River was channelized down below it, it causes the Cane Creek, channelization works its way upstream and causes Cane Creek to look like it does now, this deeply incised river. Basically, effluent. Now this is material that we use large rivers as sewages, disposal, and all sorts of stuff. We also use it for drinking water. There's something wrong with that thinking. And finally, water is removed from large rivers as part of irrigation. If you look at the Colorado River, by the time it gets down to Mexico, it's a little tiny trickle, because there's not much left of it anymore. So it's all been pulled out. Okay, so practical definition of what makes a large river a large river. One of those is it deeper than a meter? You know, pretty much you start finding places where it is at low flow, it's deeper than a meter or more. Some people call those large rivers. If you're working on it, you need a boat. This is when I worked on the Mississippi River. This was my sampling boat here. The other thing about it, again, like I said before, large rivers tend to have on the order system are 6 and above. Okay. Now remember this. This is just contrast a large river from a small river, okay, streams. Okay. So that we talked about this when we met on Monday. So gradient, it's steep, and the streams that are normally studied, they tend to be deep, steep gradient streams. There are a lot of small rivers in the prairies and all that don't have steep gradients, but the ones that are normally studied are steep and up in the mountains. Okay, the hydrology, in terms, and I've talked a little bit about hydrology before. It's very stochastic or flashy. What does that mean? Is that the river shoots up and down. The hydrology, the amount of water, the discharge changes unpredictably. It's basically whenever it rains, you have a rain event. The geomorphology of these systems, they tend to be narrow with a closed canopy all over the top. Okay. And if you walk in these streams, if you're walking down the streams, how do the habitats change? Well, as you're walking down the stream, you get big changes in habitat. I'm walking down the stream, I'm coming through a riffle. Okay, a riffle, high velocity, high substrate, or high particle size, and then suddenly I'm into a pool. That's a big change. And from the pool, I'm suddenly into a riffle. Goes side to side. Now, big changes go downstream. So if I walk down the middle. But if I walk from one shore to the other, if I walk from the shore here, I jump in this riffle and I walk across, it's riffle all the way till I get to the other side. No change. If I jumped into the pool and walked all the way across here, it's pool all the way. So I get big changes lateral, or up and down in the stream, no change sideways. And so each section of the river, I have a complete reach of riffle, a complete reach of pool. No big changes. There's a reason why I'm telling you these things. So, people who studied small streams, the defining document was this paper called the River Continuum Concept. So people describe this basically how large rivers work. And what they're showing you here is what across the side, this sort of fanciful shrunken river here, from very headwater stream, first order, second order, third order, fourth order, fifth order, sixth order. This is where large rivers begin. 7, 8, 9, 10, 11, 12. So if such rivers exist, what they would notice is there was basically, they see what they were feeling was that the rivers was a connected thing. The upstream was what happened in the upstream determines what happens in the downstream. That's what they're thinking. Okay. So here's another picture of it. It's a little prettier picture of what's happening here. Okay. The paper was written in 1980. Robin Van Oak, who was the lead author, and probably the other 6 authors were some of the greatest names ever in stream ecology. People I had as my professors, and just very, very, very famous people. Okay, and basically, it was a way for understanding how rivers work, understanding what's happening here. That basically what they're saying is, I know what's going on in a large river because I study the small streams. Okay. So they were telling people what is happening in a large river based on high gradient, flashy forested streams. Okay. And basically what they were talking about is that in the food source for in large rivers, and I mentioned different food sources when we were at the lake before. Why would no one ever calls me? Oh, can't answer that. Somebody wants dead to think. So. Anyway, so basically, with these, the organic matter, the basic food source in these streams is leaves that fall into the stream, and the term we use for leaves that fall into the stream, we call that coarse particulate organic matter. Okay. So the food source in these high streams. Why is it that? Well, the streams are shaded. There's no phytoplankton in those systems. So because it's shaded, and so you have coarse particulate organic matter. Because you have coarse particulate organic matter, you have insects that eat coarse particulate organic matter. Primarily, we call them the shredders and the collectors. Okay. And as you come down a little farther downstream, because it's still shaded, you're still not getting a whole lot of algae. Down here, though, the leaves have been broken up already. So the food source down here is not coarse particulate organic matter, it's fine particulate, whatever is passed from the upstream. Then they show the river opening up, and as it opens up, then they start saying that the periphyton, or the algae, becomes much more important down here. And so these systems tend to be dominated by filterers that basically filter the water to get their food source. So this is all nice and good, but the people who came up with this model probably never looked at a river any larger than 4 or. So basically what they were saying is the upstream dictates what happens downstream, that you have a predictable change in communities as you go. But nowhere in here did they say anything about the fact that river discharge changes. It's not just basically a simple pipe that comes through. They didn't worry about discharge because you can't really, and these streams, yeah, sometimes high, sometimes low, it has nothing to do with it. They assumed the large rivers were pretty much constant. So they missed some very important features of the rivers. Okay. And basically, when people started looking at large rivers, what they found is they don't really fit this way of thinking. Okay. So, remember, so they've been studying rivers that have a high gradient. Large rivers generally have a low gradient. The hydrology is not flashy. The hydrology is very, very predictable. If I want to see the Mississippi River in a flood, what season do I go look at the Mississippi River? Spring. Spring, we all know that. If I want to see the river low, when would I go? Right now, yeah. So in the summer, there's a very, very predictable season pattern. The canopy is wide open, okay? So you're starting to think, okay, algae is important. No, it's not, because the stream has high sediment loads. So the light doesn't penetrate because of that turbidity. And if you look at a river from upstream to downstream, so if I look at the Mississippi River, let's say, at St. Louis, and then I look at it again at Memphis, and then I look at it again at New Orleans, it's getting bigger, but the habitat isn't changing. So upstream, downstream changes in habitat. I'm not making these big leaps from riffles to pools to riffles to pools. No, I get channel the whole way down. But if I stand on the shore and go across a river, I go through all kinds of habitat changes. Main channel, side channel borders, sloughs, backwaters, floodplain, all these sort of things from side to side. So the very structure of a large river is completely different than a small stream. Wholly different set of rules. Example, so of some of these things. Here's a main channel. Here's channel border areas here. These are backwater sloughs, backwater bayous, backwater sloughs. I get all these different habitats, and just by taking my boat laterally across the river. So the habitats are laterally oriented and not up-down oriented. And then again, the river itself, the hydrology is extremely predictable. This is the average flow of the Mississippi River at the Memphis gauge. Okay, now, for all those who think I can't spell, this is how you spell gauge for rivers. Hydrology, there is no U in it, unless you're in England, because I tried to publish a paper once in a journal that was based in England, I had to change that. Anyway, and this is what, if I look at the average, it's very predictable. In the winter, it's somewhat lower, but then I get the spring rise, but summertime comes around and the river is very, very low, and then it comes up again a little bit, so I have kind of a lifted area in the winter, a big lifted area, or the fall and winter, I should say, because it's getting into fall. Fall and winter, it's basically a big lifted area, and then summer is very, very low. Spring's high, summer is very, very low. Okay. This is extremely predictable. That's how the river, it's been doing that for millions of years. Okay. If you have an event that's been happening for millions of years, you have selective pressure. Things are going to adapt to this pattern. Okay. So this river has what we talk of as high secondary productivity. The river is full of insects. They're primarily filter feeders. Okay, and so they're eating organic matter. But then everything else in the river either eats those insects or eats what is eating the insects. So the food base is particular organic matter fed by five filter feeders, and which is then feeding huge consumer communities. The Mississippi River has a massive commercial fishing operations. The waterfowl that come through every spring, huge. All these things are feeding on what's available along the Mississippi River. So something's going on feeding that. Okay. The other thing is where you find this productivity, where you find those insects. It's not, all along the channel. Where you find them there's basically hot spots. So if you get in the river and you're near aquatic vegetation beds, you get a lot of insects. If you're immediately downstream from floodplains, you get lots of insects. If you have backwater habitats that are almost lentic-like, you get them there. Where you don't get them is the main channel. The main channel is basically a biological desert. Keep that in mind. Where did the water that's in the main channel come from?
From other streams?
Upstream, right? So the whole idea behind the river continuum concept was we're providing the upstream areas and providing food for the downstream. No, it's not. It's just going right on by through the channel. Okay. And also, the primary productivity is extremely high in the spring. That's when you get all this insect activity, right before they all emerge out of the river. Okay. So, river continuum concept, when people try to apply it to large rivers, you got real problems. Okay. So, according to the river continuum concept, the energy source, the organic matter, is coming from up there to feed the lower river. In reality, the water in the main channel stays in the main channel. It doesn't come out. Where is the productive? It's away from the channel. That's not the source of food. Anything in the channel is just flowing down the stream, nothing is using it. It's moving at a speed of 2 or 3 meters per second over shifting sand. There's nothing there. Okay. Large rivers are also full. Our river continuum concept suggests that phytoplankton, algae, becomes extremely important downstream. In reality, no, it's not. river phytoplankton is not very important, not too exciting because the river is so dirty, and it's dirty from natural. Okay, so what is fueling that? What is fueling where does the food source come from? Okay, and this was written by river ecologist. Jung worked on the Amazon River. Another guy was Bailey. Bailey worked on the Orinoco, and Sparks, my boss, worked on the Mississippi. And the three of them came up with what is known as the flood pulse concept to explain how large rivers work. Okay. So the tricks here was they said, this is what you're missing. You're missing the fact that the hydrology is predictable. And you're missing the fact that there's habitats to the sides. That there is a floodplain. Okay. And what's happening on that floodplain is much more important than what's happening in your stupid little streams up in the mountains. Okay. And so this was a completely different way of thinking about rivers. And I've sort of mentioned this to you already. Okay. So floodplains are not land near rivers that are sometimes wet. Floodplains are a part of the river that is sometimes dry. This is the basis of the river continuum, the flood pulse concept. This is the whole way of thinking about large rivers. If you think about them this way, everything makes sense, except levees and the sort of the damage we do, and why rivers act like they do now that we perturb them. Okay. So what it is what makes large rivers work is that the floodplain and the river itself are joined predictably at some times, and sometimes they are split predictably. And joining, this is what makes large rivers work. I hook them together, I couple them, and they're coupled by flooding, and then I decouple them by low water. And all that timing is very, very critical. Okay. So let's look at the lower Mississippi River since that's close to us. So in the spring, it's high water. Okay. So the river and the floodplain are strongly coupled. Okay. Organic matter that's been out there over winter is now going to enter into the river, and you get this big burst in insect life right at this time of the year. So high secondary productivity exists during this time of the period, spring. So things get started. Okay. Summer, those insects that were in the river are no longer in the river. They're up flying around. They're out of the river, they're laying eggs, not much going on here. And the floodplain and the river are decoupled. The water is low. What's going to happen when the floodplain gets low? You're going to get all sorts of organic plants that are going to start growing like crazy. If you've ever walked on a floodplain of a large river, it's almost impossible to get through it because of all this growth during the low season here. Okay. So, secondary production, of course, the insects are getting hammered by the fish during this low time period. In the fall, of course, leaves starting to fall off the trees. They're landing on the floodplain. Seeds are developed, and the river comes up slightly, just enough so that some of those backwater areas are flooding now, and the migratory waterfowl are taking advantage of this. Back here, when the river was high in the spring, the fish spawn on the floodplain. They don't spawn in the river. They come out on the floodplain. And so the timing of how long they're predictable, you know that basically through evolutionary adaptation, they take advantage. They know how long the flood's going to be because it's predictable. So they go out on the floodplain, spawn, produce their offspring, and then once the river goes down, the offspring can go back into the main channel of the river. So again, everything, all the life is tied to this idea that the flood is predictable in the spring, and there's low water in the summer, semi-high water in the fall and winter. Okay. So again, during this time period, organic matter is breaking down and just laying on the floodplain. This will then be the food source for here. Okay. So, how do we manage large rivers? And this is how rivers work, or at least I maintain that. I did a lot of work on the flood pulse concept. Okay, dams, impoundments. Okay. so starting with them, what do they do with this whole deal? Okay. We look at what I call traditional dams or hydroelectric dams. What they do, you put up a dam and the area is permanently flooded. So water levels are held constant. What happens next is the water that tends to be released from these dams is released on the bottom of the dams. Dr. Green would talk about the hypolimnion yet. Okay. So you have the hypolimnion water. That's what's being released from these dams, cold and anoxic, no oxygen in it whatsoever. So that's basically killing life downstream, and fish can't use the river anymore because it doesn't exist anymore pretty much. This is when we think of dams, what we think about. Dams on the Mississippi River are different. Okay. They're navigation dams. The purpose behind a navigation is that basically when the river is running full bore, full blast, like it is. It's not in this picture here. When the river is running full blast, they drop these gates, open them up, because there's no reason to hold water back. When the river is low, they hold water back. The idea is to be able to float boats. Okay. So what they've done is, remember that flood is supposed to be predictable. It's no longer predictable. What it is now, there is no flood. So you're holding the water all the time. During the winter, during the summer, when the river falls low, the dams don't let it fall low. There isn't that summer low flow anymore. They're holding water back so that you can float the boats. Agriculture. Okay, agriculture, what's happened here is this was all floodplain at one time, which you're looking here, and this levee has been built to separate the river from the floodplain, so it can be used as for farming. So these are called levee and drainage districts. Much of the farmland around here was originally floodplain. So once you put up a levee, the river, I could say basically it's permanently decoupled. It's not permanent. Now it'll flood, but this floods will be deadly. But that water that would normally, if you had a regular flood, that water would move out into the floodplain and it'd be held, so that the water coming downstream is no longer this massive flood. It's water storage, so there is no water storage anymore. Okay. Next thing that happened is the rivers have been channelized. Okay. So straightened up to cause them to drain faster. Well, remember that the river has been flowing. Why the river goes where it goes is that's the lowest place. When you channelize a river, you separate the lowest places from the non-lowest places, and you get these huge areas of ponding, which may not sound bad, except that things die because of that. Trees die for that. This is a stream channel here. Okay. Straightening the tributaries. The purpose was water removal. Get water out as fast as you can. Impacts, though, it backfired. Okay, there's no flood storage. Quicker delivery to large rivers, and then something called head cutting, which you're looking at here. What happens is when you channelize a river, the water starts moving faster. And so it only channelizes a portion of the river, starts moving faster. We don't have any rock. Okay? We have all this soft material. And if I channelize the river, basically I've made a waterfall. Well, that waterfall doesn't stay where it's at. It's going to start eating right at the edge of that. And the river goes from being a small little river to becoming very, very wide and very, very deep. Our rivers look like they look like because they've been head cut. So again, that break point is called a nick point, where when a river goes over a waterfall, that nick point is rock, and it's fine and dandy. It's impervious to erosion. But our silt and loess soils around here are not, and so it digs down. So this river here, this is temporary flow. You're looking at the head cut. It's slowly moving its way up the stream here. So that's why our rivers look like they look. So the floodplain now, of course, is big. It's primarily for farming. Lots of agriculture being done on this. So another addition is here. This is what's called tiling. Remember, farmers want to control how much water is in. Agriculture needs to control how much water is in areas. You don't want water standing there. So what happens is the fields are what is called tiling. So they dig down in the fields and they put pipes, perforated pipes, so that when a rain comes, it goes into these pipes. What happens to the pipes? They're delivered to the river. So again, you're delivering more water faster to the river. In that water, of course, I moved this lecture, I'll come back and talk about it later, but fertilization, herbicides and all that are in that water, and that's being delivered to the large river, and we're gonna talk about some of the problems that causes. That's on a global scale. Okay. So basically what's happened is to disrupt the predictable hydro period, now water is hitting the river much faster than it was before. And because of navigation, all those seasonal patterns, highly seasonal patterns are gone. Okay. The river and the floodplain aren't coupled anymore. Levees keep the water out. Okay. And so the river's no longer, the floodplain is no longer stores water on it. And within the river, you're getting out in those side channel areas and all that, those are all sedimenting in. Any place the river runs slow quickly settles in. And so what's happening there is you've lost all this primary productivity that's been going on, and you've lost the ability to store waters. So when large rivers flood now, this is a levee blowout. What you're looking at, this is the levee material. These are highly destructive floods now. I talked about that before. There's nothing natural about a flood anymore. The natural flooding, the river rises slowly, goes out on the floodplain, stays there for a while, comes back down. Not these big, massive blowouts that we have nowadays. So I'm finish up here on this. So right now, large river management is trying to deal with a lot of these sort of things. Navigation, starting to take these into consideration with each other. There's been some neat things that have changed on the Illinois River, which is just north of us here. They've been moving setback levees, making more active floodplain, reclaiming a lot of farmland. There's a big natural, wetland area called the Amaquan. When I lived in that area of Illinois, it was one of the biggest farms that ever existed. Now it's a massive wetland, and people go there to see what it's supposed to look like here. So basically, with some of the examples we hear, they're trying to return the hydrology to the Colorado River. It's heavily dammed, but they're timing the dam releases to make it look much more seasonal. Dams are coming out. Columbia River primarily, a lot of that's in support of the salmon fishery, which is in a lot of trouble. Setback levees, which I just mentioned, and in buying out farmers on floodplains, said we're going to put some of this back. And dechannelization, I have the Kissimmee River because it's a Florida river stuff, but there's dechannelization going on right now on the Obion River, and Dr. Blanchard is doing a lot of great work. With his people looking at how aquatic communities are responding to dechannelization. Okay, and on the Mississippi River is trying to building habitats right in the river to try to help some of this other stuff. Okay, I'm going to stop right there. I may save this for some other time here.